Okay, hello everyone. How are you doing? Okay. How is San Francisco? Are you good? Maybe yes. Okay. New Jersey, are you good? Okay, so do you have any questions for me before we start? So before we get into the week 4 slide set, I want to finish our discussion that we had in our third week, last week. So I briefly talked about at the end of the last class, where I was talking about, some issues that they may arise when you are doing the hypothesis testing. Now let me start with one example so that you can understand what are the possible issues that you may get when you're performing a hypothesis testing, or in general, when you are conducting a statistical inference. So I want to ask, who remembers Paul the Octopus? Or who have heard of the Paul the Octopus? Yeah, that was in 2010. Okay, some people, they have heard of that octopus. So that was a story about one octopus. That was in 2010 regarding the World Cup. And then what happened is that they had that octopus, they present to the octopus 2 boxes with food, and they also have the flag of the country, let's say, on that box. And then the box that the octopus eat the food first, they said that that's the team that is going to win the game. So the Paul the Octopus actually correctly predicted the outcome of 12 out of 14 national soccer matches. Now that's kind of impressive, right? For an octopus to be able to predict 12 out of 14 national soccer matches. Okay, now let's try to use some statistics and try to understand and see the different probabilities. So let's assume that Paul was no better than a coin flip. So in other words, their guess was a random guess from the octopus. Now I want to find what is the probability of flipping a coin 14 times and getting heads 12 times or more. So in other words, what's the probability that the octopus, if it makes random guesses, it's gonna get 12 out of 14 times. Okay. Now, to find that probability, let's say I want the probability of getting 12 correct answers, then that's a binomial. But even if you don't know the binomial distribution, that's like a very simple formula here. So then you have, let's say, the probability of correctly identify the team is 1/2 is 50%. So I want 12 of the times to be correctly identified. That's a probability. And then I'm multiplying with the probability of not correctly identifying the country. That's again 50%, 2 times. Now I'm also multiplying here with a coefficient. This is giving you all the different combinations that they may exist. For example, maybe the octopus predicted the first 2 ones, let's say the first 12 ones correctly, and then the last 2 ones to be wrong, or maybe he predicted the first 2 to be wrong and the other 12 to be, and any other combinations, okay? That's why we're multiplying with that combination in front of those fractions. So then we get the probability. We do the same thing for what's the probability is going to predict, let's say 13 out of 14 times, again the same logic, and then what's the probability is going to predict correctly 14 times out of 14. Now the probability that is going to predict, let's say 12 times or more is actually 0.0065. That's quite small probability, right? So it's 1 in 155. Okay? But that octopus predicted the correct, it's very unusual, right? For that event to occur, right? Now, this is the calculations that, let's say 2 math professors did when they conducted to tell their opinion, let's say about the Paul the Octopus. Now, let's add some more information in our calculations. So, okay, we have 12 out of 14 predicted correctly. Now, we know that Paul usually predicted games involving Germany. Okay? So 13 out of 14 games involve Germany. Then the octopus had a bias towards Germany. So in other words, he predicted 11 out of 13 times that the Germany team will win. And actually Germany has a quite good team, and they won 9 out of 13 games. Now let's reevaluate the chances that the octopus will correctly guess the winner of the game. So here what I'm doing, I'm getting, let's say, what's the probability that Paul would predict that the Germany will win times the probability that indeed the Germany team will win. And then I'm adding the probability, let's say, here is when Paul will not predict that the Germany will win, and actually indeed Germany will not win. Okay? So these will give us that 0.633. So that's now the probability of correctly guessing the winning team. Okay, now let's redo our calculations. So I want, let's say, what's the probability that the octopus now is gonna predict at least 11 games out of 13 games. Okay? So I'm doing the same kind of calculations. And then again, even in this case, I'm going to get a probability of 0.091. So 1 in 11. Okay? So it's much more likely compared to our previous calculations. Okay, what does it mean? Does it mean that indeed the octopus has the ability and has maybe the knowledge or something to predict, let's say, the winner of the game? Now, even after the previous probability, we may still be a little bit skeptical about the results. How can an octopus be able to predict, right? Now I'm adding one extra information into our discussion. Let's say, what about there were 10 octopus in that aquarium, okay, that they were trying to predict the game. Let's see what is the probability that at least one of the octopus will predict the winner. Here, let's say the probability at least one octopus will be as good as Paul. To find the probability, I need to do 1 minus the probability that, let's say, none of them will predict correct. So 1 minus, that's the probability that I found before. Again, 1 minus that probability to the power of 10. Let's say I have 10 octopus, and then this will give us a probability of 0.614. Okay, now that probability is quite large, right? The probability of at least one of the octopus will predict the team correctly. Okay, now imagine, now we're talking about, let's say there are 10 octopus, but you know there are also other animals. So I have heard stories about different things like hippopotamus or different kind of animals that they're trying to predict the games. Now, if we incorporate that information into our analysis, then we can see that, you know, by random chance, it may not be unlikely for one of those, let's say all the animals that they're trying to predict, that they're going to identify correctly the winner of the game. Okay. Now, do we still think that the Paul the octopus had that ability? Maybe no, right? In the sense that, you know, by random chance, if I repeat the experiment many, many times, there is a chance, and actually that's quite large probability, that you're going to see, let's say, find an animal that will identify, I don't know, 11 out of 13 games correctly. Okay? So why I'm doing that discussion? So the same logic also applies when we're doing data analysis and in general in, you know, the research. Lots of research results are just like Paul the octopus. So they look impressive, they have very small p-values, but we don't know how many other tests were conducted and not revealed because they were not interesting. So in other words, if we over-compare, so in other words, if I conduct a lot of hypothesis testings, and I underrepresent those results, so in other words, I'm not really presenting all the results that we're getting, then we're getting the picture that I'm going to describe here, which is kind of a misleading picture of the situation. For example, I have this scenario, that's, let's say, the estimate that I want to estimate. Of course, I don't know what is the value for the estimate. And let's assume that these are all the estimates that you may have. Okay. Now, the problem that may arise is when only, let's say, these estimates, they give significant results. So in other words, the p-values are quite small, and then we're going to reject the null. Then, if we only report these ones, then we get a quite different impression of the reality, right? So here, if I'm only reading papers and all the values are around here, then I got a very different perspective of the reality, right? even though the estimate is close to 1, because only these papers are really published and I'm reading them, then I'm getting a very different sense. Now I'm thinking maybe the estimate is somewhere close to maybe 2 or 3, but that's not the case. The main reason is because of what you call the publication bias, right? So the takeaway is that if we are, let's say, over comparing, if we're conducting a lot of hypothesis testing, by random chance, we may get some of them to be statistically significant. So it's very important to find a ways to overcome that issue and also be transparent and report any results that we may get. Now, 2 ways that the publication bias can arise. The first one is what we call the p-hacking. So that's an analyst knows that the result is much more interesting, exciting, publishable, if, let's say, the result is statistically significant, if the p-value is less than that threshold, the 5%, they play around with the sample, they're choosing specific type of people, specific type of experimental units until they get significant results, okay? And then they report that results, okay? So p-hacking is also kind of unethical, right? Trying to find, modifying and repeating that again and again until you get some significant results. And then we also have that p-screening. So let's say an honest researcher there formulates the hypothesis and conduct the test. However, the statistically significant results are more likely to be written up, published, and publicized because these results are more interesting. So it will not really be interesting to have another, let's say, another paper saying that this medicine is doing nothing for that specific disease. Okay, so that's why we may get into that issue that we don't really report all the results that we get, and we get one, let's say, paper that shows that that specific medicine is doing something, but we don't really know how many other studies they have done regarding that medicine that doesn't really show any effect, right? Any significant results. So in both of these cases, we may end up with a lot of false positive and overestimates. So to overcome those issues, there are a lot of remedies as statisticians that are trying to inform the researchers and try to encourage them implement those remedies. For example, maybe try to reduce your significance level, depending on the case, reduce that threshold, the 5%. A lot of cases we may need to adjust our p-values if you do multiple comparisons. Also, one thing that I'm very interested in, and I really want people to start doing it, is reporting the confidence intervals, not just the p-value, but also the confidence interval, so you can get an idea of also the variability, the spread around your estimates. And of course, you need to be able, if someone else wants to get into the study, to, let's say, replicate and get the same results. Okay? Any questions regarding the p-hacking and the p-screening? So that's very important, and that's kind of related to what you will be doing even with your projects, right? You may get some results that are not statistically significant. That's fine. Okay, it can happen. That's not a problem. You can write it up and present your results. Yes?
Would it still be considered p-hacking if you change your analysis rather than the data that you're performing an analysis on?
So again, it's kind of a p-hacking in the sense that, so you know there are maybe 10 different methods to get a result. By random chance, again, there is a chance that you may get some statistically significant results if you apply all those 20 methods in your data set.
Yeah.
So what is better is you need to look, let's say you get the data, you decide about your methodology, and then you apply. You decide based on the characteristic of the sample, the characteristic of what's going on, what do you think is more appropriate, and then you apply the methods. Yes?
So, for example, when we did the housing prices by location, right? So what if you go through the analysis and you realize, wait, this all looks backwards because I must have missed something, or I missed a variable that should be included that's confounding.
Okay, that's not a p-hacking. So that's more exploring the data and see some trends and some confounding variables.
So it's also in the reporting.
Yes.
Okay.
What I'm saying is that, for example, you want to do, let's say, regression, and then there are 10 methods available, and then you just try all the methods and see if some of the methods will give you some significant results. Now, planar, right, it's more about exploring. So I would say that it's more in the kind of exploratory data analysis where, oh, you may thought there is a confounding variable, let me also try it in the model and see what I get. I would not consider that as p-hacking. Any other questions? Any questions online? Okay, so if you don't have questions, let's continue. Let's go in week 4. Okay. Now we're gonna try to get into more advanced methods, some methods that can help us in different settings, in different scenarios. So what we're gonna talk about in this set of slides, first we're gonna talk about what do we mean by machine learning techniques, machine learning methods versus the statistical methods. Then we're gonna talk about differentiate, let's say, between the regression problems and the classification problems. And then we're gonna talk a little bit more about the classification problems. We didn't talk about in the previous lectures, we're mainly talking about regression, and we're gonna get into the classification problems, see the logistic regression, decision trees, and then the last one, depending on the time that we're gonna have, we're gonna talk about the k-means, the method for clustering. And of course, we're gonna start doing that analysis using R and RStudio. Now, before we get into, let's say, the actual methods, now let's get a general idea of what we mean by machine learning techniques. So I'm sure you have heard about machine learning methods, machine learning techniques. Now, what is the difference between the machine learning techniques and the statistical methods? So the main difference is based on the goal, the ultimate goal of those techniques. Using the statistical methods, usually we focus on the inference, on statistical inference. This is what we're doing in the previous weeks. We're trying to see what's the relationship between different variables and then try to do some inference regarding the slope, regarding different parameters in our model. On the other hand, machine learning techniques, machine learning methods are more focused on what we call the prediction. So I want to build a model so that I can use that model to predict or forecast to some unseen data set. Okay, that distinction here is not strict in the sense that there are some statistical methods that they can help us do predictions. And actually we have seen examples, the linear model, right? We could use a linear model and we could get some accurate, quite accurate predictions. And also there are some machine learning techniques that sometimes they may give us the ability to produce some kind of inference. Okay? And we're gonna see, let's say, the decision trees. Again, there we should be able to get some sense of the relationship between the variables. Now let's specifically talk about those different methods. Now, typically in statistical methods, we work with what we call the parametric statistic. So first, what we are doing, we are specifying the model in advance. We are defining, let's say, the variables that we have in our model, and then we use our data to estimate the parameters in our model. Examples, let's say the linear model that we had before, we specify the linear model. Of course, we are allowed to do some exploratory data analysis and came up with some more variables in the model. But then once we decide about the model, we get the data and then we estimate, let's say, the different parameters. Similarly, when we're testing for the population proportion, do you remember we're talking about elections? I wanted to estimate the proportion of people that they're gonna vote the Republican candidate and the proportion of people that are going to vote for the Democratic candidate. Again, it's kind of the same logic. I set up beforehand, and then I'm getting the data, and I'm performing the test. Now, what are the advantages of that statistical method? The first one is can often be used with relatively small sample size. When we're defining those statistical methods, we usually make some kind of strong assumptions about the model. We didn't really talk a lot about the assumption in this class, but for example, we make a discussion about you can apply the linear model when there's a linear relationship between the variables. Also in the linear model, there are some other assumptions, let's say normality. There are a lot of assumptions that we require from our statistical model. And these help us to do, let's say, inference, even if we have, let's say, a small sample size. Then we have high potential for inference, again, because of those assumptions that we're imposing, that specific format for the model that we're imposing, we have the chance to perform some statistical inference. So it's very easy to compute the linear regression. I show you even close form for the coefficients, for the estimates for the coefficients. We have very close forms for all these, and then using technology, it's very easy to get, let's say, the different estimates for the parameters. Now, the disadvantage of the statistical methods is that if the underlying model is wrong, so in other words, if any of the assumptions are not satisfied, let's say if you have data that are not linear and you're applying the linear model, then the results are kind of meaningless. You can still apply the linear regression, let's say, even if you don't have, let's say, the linear trend in the data. You can still apply it, but you cannot really trust the result that you're going to get. The result that you're going to get, they will not have any meaning. You will not really be able to interpret the results from your model. Now, on the other hand, let's see in general, what are the machine learning techniques? Some of them are machine learning techniques are basically creating some functions that approximates the trend in a data set as closely as possible. Okay? So usually we don't really make any assumptions about the form we don't make any assumptions about the form of the function. We're not going to say it's linear, it's quadratic. We just have the data basically decide the format of the function. So the model usually can be very flexible and it's driven by the data set. The resulting functions are often algebraically complex. So usually in the machine learning techniques, we're not going to have closed forms for the different parameters or the model. And that's the big discussion that we have. I'm sure you have heard of that machine learning techniques. Some of them are more like a black box method in the sense that I give the data, I don't really know what's going on, how it works, but then I just get the output. And again, it's that a big discussion about, okay, if I have a method that I'm not really sure what's going on there, I don't understand what's going on there, but it gives me pretty accurate results, should I use that one, or do I prefer a method where I understand what's going on, but I don't give such high accuracy? That's like a big discussion. There are also ethical issues. There are many things going on behind this, but machine learning, not all of them, but a lot of them are more like black box methods. I'm not sure how they work, and then I'm just giving the output, and then I get the output. The advantage is that given enough data, we can get very accurate predictions. They're doing a pretty good job approximating or summarizing the trend of the data. The disadvantage requires a significant amount of data. We need data to get accurate results, and then we have limited ability to do inference because I don't have closed forms for the different parameters or the different things in the model. It's very hard to do inference. This may not be a problem if you don't really care about inference. If you don't really mind to understand the relationship between variables, no problem. If your goal is about predicting, get accurate predictions, then maybe that's not even a disadvantage of the machine learning techniques. Okay. Now, any questions? Now, the machine learning techniques and the statistical techniques, roughly speaking, are categorized into two big groups of methods, or let's say two big groups of problems. The first one is what we call the supervised learning. So these are kind of techniques, algorithms that maps an input to an output. So I'm going to have a clear response variable. I'm going to have a target. I'm going to have a variable that I want to study, that I want to predict. Okay? And then I'm going to use the input. I'm going to use my explanatory variables to predict, let's say, those outputs. So some examples of the supervised algorithms are, for example, the linear regression. This is what we've covered. We have the response variable, our y's. Okay? It's clear, I have a quantitative response, and I want to predict that one, given some values of the explanatory variable. Today we're going to see the logistic regression, and then there are a lot of other techniques that are under the umbrella of what we call the supervised learning. Then we also have some techniques regarding the unsupervised learning. So here is, we don't have a clearly defined response that we are trying to predict. So I will not really have that response, that target variable. So the unsupervised, I will consider it more kind of part of our exploratory data analysis. So I don't have really a target that I want to know, but I want to get a sense of how the data look like. Okay? And here I have the K-means clustering, and there are more, the neural networks, there are a lot of other techniques that are under the umbrella of, let's say, the unsupervised learning. Now, to apply those more advanced algorithms, usually we need to know to code in languages that are more advanced compared to Excel. And you can use Python, you can use R, you can use RStudio. Now in this class, we're using the R and RStudio because it's free. So the high school students can download the R and RStudio for free. It's kind of easy to learn. First, it may be a little bit, let's say, weird if you haven't coded before in R, but once you get familiar, then it's quite natural and quite easy to learn and use. It's very popular. Most of the statistical methods and techniques, machine learning techniques, they are released first as a package in R and RStudio. So it's free, as I said, it's open sources. There are a lot of high quality packages that we can use. And R is a complete programming language. So the language that we'll be using will be R. So here I have a link to download the R. And then we're also gonna use the RStudio. The RStudio is an integrated development environment. How I like, and here I also have the link, how to download RStudio. How I like to think about R and RStudio, I want to think R as like the engine of a car, right? So this is our programming language, that's the software that I'm gonna use to program. But of course, if I need to do something with the car, I don't really go on the engine and try to modify different things, right? To start, let's say, the car. What I'm going to do is I'm going to use the dashboard. So the dashboard is much friendlier, user-friendlier to, let's say, get the things that I want from the engine. So this is our RStudio. So the RStudio will be the dashboard. We're going to use the RStudio to code. Is a much friendlier environment where RStudio uses R as the programming language. So we need to have both of these programs installed on your computer. So were you able to install R and RStudio? Did you have any issues? Let's say even the people that are online, did you have any issues with downloading R and RStudio? Okay, so let me pull up a lab. So I'm using the lab for my classes, for my data science classes. That's an introduction to the R and RStudio. So if you haven't used R and RStudio before, this will give you a brief introduction to what is R, what is RStudio, and I'm also having here also the links to download and the steps to download the R and the RStudio on your laptop. Now, before we get into the techniques, what I want to do is, let's open the RStudio. So on your laptop, you should be able to see both R and RStudio, okay? So that's R and that's the RStudio. So what I want you to do is, I want you to click to the RStudio and get familiar a little bit. Let's familiarize ourselves with the RStudio. Now, once you open RStudio, I want you to observe that we have 3 different tabs. So here I have the tab called the console, and then I have here a part which is set environment, and then another part here which is set plot. Okay? Now the console is the area where we're going to do our coding. For example, maybe I want to do, I don't know, 2 plus 3. Okay? R will give me the result. Okay? Or maybe you can do 2 up. Let's say 2 times 3. Okay? Again, R will give me the result. Now the good news about R is that it's object-oriented, which means I can define objects. I can define variables that take values. For example, I can define x equals to 3, and let's say y equals to 2, and then I can do calculations with those variables. I can say w is x plus y, okay? And then I can call w, and then I can see the value, okay? So the console is the area where we're gonna code. Now let's see the other tabs. So the tabs here on the right that will be of interest, the first one is the environment. Environment here, you can see the values of all, let's say, the variables that you use, that you define. Here we define a variable x, y, w. Now you can see the variables and you also see the values of the variables. Also, you may check the history. So the history here is showing you all the commands that you run, okay, before. So these two will be of interest in the RStudio. And then at that bottom tab here, the first one, you have access to your files. Here in the plots, if you create any plot, then it will be showing you here. And then here we have a tab regarding the packages that you have for the RStudio. And I'm going to talk later regarding the packages. Now, another benefit of the R is that there are some built-in functions that we can use. For example, I may get, let's say I want the logarithm of 10. Now there is a built-in function in R called log that you can run it, and this will give you the logarithm of that number. Okay? And there are also a lot of functions. There's the square root, right, of a number, sqrt. So it's very important to know the name, the precise name of the function, okay, so that we'll be able to call that function in R. Okay? So these are what we call functions. And there are some built-in functions, and there are some functions that are in a collection of more functions, a data set, which we're going to call packages. Now, another thing that I want you to know about RStudio is that, okay, here we're writing the code, right? But what happens if I want to stop, let's say, coding, maybe I want to make a break and come back. So I want to close my RStudio, and then I want to go back after maybe an hour to continue with my data analysis. This code may disappear. So what we're going to do is we're going to use kind of a notebook where we're going to add our code. And this will be the R script. Okay? So here, if you go to add and the R script, then you're going to have that tab here. And we can use the R script to add our code. For example, I may add R +3, +3. Basically, all the commands that you had before, you can just write them here. And anytime, let's say you access the RStudio, then you can access your code. Of course, you need to save it. So once you create it, you click save. And then, okay, you go to your folder that you want to save. Maybe I'm going to save it as a sample code. You save it. Now, anytime I want to access my code, I go within the file and then double click on that R script, and then this document will show up. How do I run the commands? You put your sensor, and then you just click the run button here. Run. You can see the sensor went on the second line. You keep running, and then you can see all the results. Okay? Now you have the code. Anytime you want to rerun it, you can just go to your R script. Now, another thing that you can make on the R script is that you can add comments. Let's say here, I want to add some comments, say maybe my first R script. So I want to remember what I'm doing. Okay, here, using R as a calculator. Okay, and then maybe here, defining variables. Now here you observe that if I use that sign, then I can add comments to my R script, and the comments become green now. Okay, so you can see that here I have a title, I have my first R script, and then here I'm explaining maybe to me or to the people that were collaborating what we're doing with those kind of code. And then of course I can save, so anytime I'm accessing that R script, I can access, let's say, my code. Any questions so far regarding the R and RStudio? So online, are you able to access RStudio and run some commands in the RStudio? Yep. Okay. Now, another comment that I want to make is that anytime, let's say you have an R script, and we're gonna see later, we want to read some data, you need to make sure that your code, the R script, and the data set are on the same folder. So you need to have your code and the data set on the same folder, okay? And then before start reading the data, we need to tell R where is the data, where can R find the data. But I'm gonna talk about that once we go to the example. Okay, so any questions regarding R in RStudio? Anything that you want to clarify? Okay, the console is the area we're gonna write our code, where we're gonna execute our code. You can use the R script to write the code so you can save it, so you can re-access it anytime you want to start working on that data analysis part, okay? Okay, so that's what I have to say about the RStudio and the R. Here you can see a guide, an introduction to the R and RStudio. Please take a look and let me know if you have any questions. Okay, another thing that is good about R is that we can get help. So for example, I use the log function, right? Let's say I get the log of 10, but I'm not really sure what log does, right? So what I can do is I can go in my console and then click and then use that question mark, and then let's say log. If you click enter, not logging, log enter, then you can see that in the help part of the RStudio, it gives you a description regarding that specific function. What are the arguments of the function? How can you use it? And usually at the end, you can also see some examples on how can you use that specific function. So all the functions that I'm going to use today, if you want to know more information, you just use the question mark and then you just type the function, and then RStudio will give you some more information. Okay? So now let's continue. Let's go back in our lecture slides. And let's see some new methods that you may need to use for your projects. So far, all the scenarios, all the examples that we have seen, the response variable is a quantitative variable. So we're talking about the number of reported crimes, the voters' turnout rates, the assessed house values. All these are numeric values, and it also makes sense to do calculations with these values. But in a lot of cases, we may be interested about categorical responses. Responses that they're not taking numeric values, but I have some specific groups or specific categories. And I remember when you are presenting the proposal for your project, some people, they have a categorical response, right? They have whether they have cameras or they didn't have cameras, something like that, right? So here, we need to consider problems where the response is a categorical variable. And here I have some scenarios. Let's say a person arrives at an emergency, let's say room with some symptoms, and then I want to decide what is their medical condition: stroke, drug overdose, or epileptic seizure. Again, I have 3 categories that I want to assign my observation. Or let's say I want to predict the type of play run in NFL, pass or rush. Or let's say I have a quality score, right? Let's say from good, fair, poor. Again, I have different categories. I don't really have a numeric value. Now, the problems that the response variable is a categorical variable, we're gonna call them classification problems. We want to classify an observation into 1 or more categories. Okay? Now, can I use the linear regression? That's the natural question that we want to ask. Okay, we know the linear regression. Why we don't apply the linear regression to the case where I have a categorical response? Okay, in general, I'm going to say that linear regression is not appropriate to use anytime we have categorical output, a categorical response variable. Okay, let me try to give you an idea why that may not be the case. Like why it may not be suitable to apply the linear regression. Let's take the first scenario. You have the medical condition: stroke, drug overdose, epileptic seizure. Let's say you want to apply the linear regression. What would you do? Maybe you just assign some numbers to those different categories. Let's say I'm defining with 1. So let me actually write it here. So let's say I'm defining with 1 if someone has a stroke, the value 2 if it has the drug overdose, and let's say 3 if it has the epileptic seizure. Okay, so in this case, theoretically speaking, you could apply the linear regression. Now the responses have numeric values, and then you can apply the linear regression. But the problem is that here you are assuming that there is an order between those different conditions. You're assuming that the stroke comes first, the drug overdose comes second, the epileptic seizure comes third. What happens if I change the order? Why I'm defining 1, 2, 3? Maybe I can define 1, 3, 2, or 3, 2, 1, right? If you change the coding of these different categories, you may get different results in the linear regression. So in this case, the linear regression may not be suitable. Now, there are some exceptions that the linear regression may be applied. For example, if the outcome is ordinal, let's say if there is a natural order in the categories of the response, and there are enough categories, then yes, maybe you can apply. So let's say here, if I'm talking about the quality score, it's good, fair, poor. Maybe I'm going to start with maybe 1, 2, 3. Now there is like a logical order between the categories. There is like, you start from the worst to the best, let's say poor, fair, good. Okay, in this case, it may make more sense to apply, let's say, the linear regression. But again, that's not the ideal, because why will you have 1 unit difference between those 3, let's say, quality scores? So why I'm not having 10 scores between them, or why I don't have here 2 units and then 3 units? So again, there's no like a thing that can tell us regarding the units difference between the different categories. Now, what happens if you have a binary outcome? Binary, it means I have 2 categories. Okay? Let's say I'm denoting with 0 the failure, and then with 1 the success. Now, in this case, things may be better, they're kind of better if you apply the linear regression. Now, in the case of a binary outcome, our response variable, our predicted response variable, will be the average of the responses, the average of the responses, the average of the predicted values will be equal to the probability of success. So if you have a linear model and you have a binary outcome, let's say failure 0, success 1, then we can show that our y hat is nothing else but the probability that you're going to get a success. Okay? So in this case, if you apply the linear regression, then if you get a number, maybe let's say less than 0.5, less than 50%, you're going to cite as a failure. If it's greater than 50%, you're going to assign it as success. But now the problem is that with a linear regression, you may get some values that are outside of the range. So here we're talking about the probability of success, but your linear model may give some predicted values that are maybe negative or greater than 1. Okay, and here I have an example. So here I have a scenario where I have 2 categories. It's a binary data set. Let's say some values are here. That's a failure. That's a success in this data set. What happens if I apply the linear regression? Here I apply the linear regression. So you can see the model. I'm modeling the probability of the y to be equal to 1. That's what I get anytime I have a binary output. And then you can see that now if I feed the linear regression, I can make predictions that are negative here. But how is that possible having a probability, right? It does not really make sense to have a negative probability in this case. What is the remedy to that one? What is the remedy? Anytime you have a binary and you want to apply a model, is use the logistic regression. And what is the logistic regression? Instead of just taking the linear combination of your data, what we're going to do is we're going to get that function of the data. So we're going to get e to the power of the linear combination of your data divided by 1 plus e to the power again to the linear relationship between the data. Now, if you apply that function, then the model now will have the following format. You're going to start from 0, and then you're going to gradually go up to 1. And then we can use that function to model the probability. And this is what we call the logistic regression. Now, you may ask me why we choose that specific function. You can choose any function, as long as you can, let's say, restrict yourself between 0 and 1, and then you don't really get any so weird predictions regarding the probability. Okay, so I got that example actually from that book. It's called An Introduction to Statistical Learning with R. Okay, that's a very nice textbook if you want to get some more information regarding the linear regression, the logistic regression, and even some more advanced machine learning techniques. Okay, that's a very nice textbook with a detailed discussion, and also it has applications with R. It shows you the R code on how you're going to perform all these different models. Okay, now let's see. Logistic regression is a statistical model that is used to predict the probability that an outcome from a categorical variable with two categories will occur given some predictor variables. Again, I'm going to have my explanatory variables, and I want to use the explanatory variables to see how it influences and how it affects my response. And in this case, our response will be the probability of getting one of those categories. And let's define the model. Let's say I have a variable x. This is my predictor. That's my explanatory variable. This is the variable that I'm going to modify and see how it influences or affects my response. My response here is a category. I have two categories, and then I'm modeling the probability of my response to be equal to 1, to be equal to the first category, to be equal to that function. Okay? And then the probability of y equals to 1 is the predicted probability that the event will occur given that value of the predicted value. Does it make sense? So now we don't have a quantitative variable, we have a categorical variable, and specifically for the logistic regression, we're going to use the case where I have two categories, and I want to predict those two categories. And this is the model that we're going to use. Now, if you do a little bit of algebraic work, then you're going to see that the logistic model can be rewritten as follows. So I'm going to have the log of our probability of y equals to 1 divided by 1 minus the probability of y equals to 1 equals to that linear relationship with our predictor. Now, this monotonic transformation, it has a name. We're going to call it logit. And this is what R is giving you anytime you try to get predictions. Usually, R is giving you the logit transformation, so giving you the value for that linear combination of the predictor. And then what we're going to do is to find the predicted probability of success, we're going to plug in the values into our formula. So this is what we're going to get from R. We're going to plug it into our formula. That's the logistic regression formula, the logistic regression model. We're going to plug in the values, and this will give you what is the probability. Now, this will be a number between 0 and 1, right? How do you assign that observation to be in the first category? How do you assign that observation to be in the second category? We're going to say that if the predicted probability is greater than 50%, if the probability that y equals to 1 is greater than 50%, then this will be categorized as a first category. So then this will be our success. So if for an observation, the probability of success is greater than 50%, we're going to assign that observation to the first group. If the probability is less than 50%, we're going to assign that probability to the second group. Yes?
Does this assume that success and failure are mutually exclusive?
Yeah. Any other questions? Yes?
But like false, so 0, y equals 0, just be like 1 minus p, y equals 1.
Yes, so here I'm not giving you the formula for the other probability, because as you said, it's 1 minus, right? If I want to find what's the probability y equals to 0, you get this probability and you do 1 minus. I use the complement rule. And this will give you what's the probability of failure. Okay? So here we just care to get the probability of one of those two events, either the success or the failure. Once we get that, then we can automatically also get the probability of the other category, okay? Because these are complement. Okay? Okay, so you can extend. Any other questions before we move? Any questions online? Okay, now I have two categories. Now, we don't necessarily have to have just a single predictor variable. You may have more than one. And let's see a question here, a scenario. Let's say you want to identify whether a voter voted for Biden or Trump in 2020 election. Okay. Here I have the response variable to be categorical. So let's say I can code with 1 if they vote for Biden, 0 if they vote for Trump. It doesn't really matter what you can assign. You can either assign 0 and 1. You just need to know which category you assign as 1, which category you assign as 0. So let's assume here that I'm assigning 1 for Biden, 0 for Trump. Now there are different predictors, different explanatory variables that they may affect, let's say, my response, whether or not they're going to vote for Biden or Trump. Let's say maybe the age. The age may really affect your voting preference. Maybe your residence, whether you are in urban areas or when you are in rural areas. Maybe your education, let's say whether you have a college degree or let's say you don't have a college degree. What we're going to do here, because I have a response variable that it's a categorical with two categories, then I can apply the logistic regression. And here the model would be, let's say, the probability of y equals to 1. This would be our response. I want to find what's the probability that someone will vote for Biden. Of course, to find the probability that someone will vote for Trump is 1 minus, okay? So it's the same thing. So here, we're gonna model it using the logistic regression. So here I want you to observe that I have the function that I'm gonna use, right? So I don't want a straight line. I want that curve function that will go from 0 to 1. But now I'm gonna have more than one predictor variables, more than one explanatory variables. So here I'm gonna have again the linear combination. And let's say I'm going to have the age, I'm going to have the residence, and then I'm going to have also the education. Okay? Similar logic, but now I'm going to have more than one variables, more than one predictor variables. The good news is that we can use R to get all this information, to get all the estimates, and also get the predictions for the logistic regression. We don't really need to do those calculations by hand. Now, if you want to, let's say, classify more than two categories, you can still modify the logistic regression. And let's say, if you have, let's say, more than two, first you decide two of the two categories. And then once you go the first category or the second, you further apply logistic regression to the subcategories of the categories that you have, that you defined before. But usually, logistic regression is applied only when you have two categories. If you have more than two categories, there are other methods, other techniques that are more accurate. They get more accurate predictions. Okay, now let's go in R and see how can we implement the logistic regression. Okay, let's go back in R. I also want to point out that logistic regression is a statistical method. Again, we define the model beforehand, right? We have a model, we define the model beforehand, and now we're going to use the data to estimate the different parameters in our model and also be able to make predictions. Now, to perform the logistic regression, what I want you to do is you can go and find an R script that I uploaded on Google, which is called Lecture for R Activity. So if you double click on that one, then you can see that I created an R script. Okay? So here I'm giving you a brief description of the data set. So here I'm telling you that we're going to use the coasters.csv dataset. So here I have information for 123 roller coasters. I have their names, the name of the park that they are in, the material of the track, the maximum speed, the highest point, the length between the largest gap and the lower point. I have the length of the roller coaster, the age, the design, whether they're flipping the passengers or not, and then let's say the number of times the roller coaster flips the passengers. So have more information about the roller coasters. Now, before we start doing any kind of analysis, we need to inform R where is our data sets. And as I said, what you have to do is you need to have a folder where you have the code, the R script, and the data together. And this is what I did here on my computer. So here you can see that I have a folder that's regarding the lecture 4. And here I have my data set, the coaster.csv, and then I also have the R code. Okay? Both of them needs to be at the same folder. And then what I'm going to do is, before start doing the analysis, I need to set the appropriate working directory. In other words, I need to tell R where is my data. To do that, what you have to do is you go in the session, set working directory to source file location. So if you click on that one, then you can see here in my command is telling R that all the data that I'm going to use is in that folder, is in the lecture 4 folder. So that's very important. If you don't set the appropriate working directory, then R will not really know where to find the data. So you go to session, set working directory to source file location. That's the first thing that you need to do before start doing any kind of analysis. Now, after you set up the working directory, now let's go and read our data set. So to read the data set, I'm going to use the function in R which is called read.table. There are many functions that can be used to read data. So here I'm choosing to use the read.table function. So for that specific function, I need to, as a first argument, I need to set to R what is the name of the file that you have the data. So in this case, the file name was coasters.csv. So you need to use the quotation marks and inside write the name, the precise name of the data set. Okay? Then I'm specifying two more arguments. So if you open the coasters, so let me open them. So if you open the coasters, let's say I want to use, let me use Excel to open them. I want you to observe that here, the first row is basically the names of the columns. Okay? So here I need to tell R that the first row it just has the names of the different variables. So here I'm using the headers function, the headers argument. Then I'm specifying that the header is true. So it means that the first row in the data has the names of the columns. So it will not really count them as, let's say, observations in our data set. And then if you open the CSV, you're going to observe that I'm let's say, separating my observations with commas, with comma. So here I'm also need to specify, I need to tell R that my data are separated with comma. Okay? And that's why I'm defining the SEP, and then I'm using the quotation, and then I use the comma. Okay? Now, if you run this command, if you run this specific command, then this will read the data set. Now, R is what we call an object-oriented language. Now, what does it mean, an object-oriented language? It means that you can define variables, you can define objects where you can save the different variables. And this is what we're going to do here. For example, I'm giving the name coasters to my data set. And if I run this command, then you're going to see that I'm creating an object in R that is called coasters. And then you can even see it in the environment. Coasters here is a data. It has 123 observations, and then it has 11 variables. Okay? So then it means that you successfully read the data into R. Any questions? Should we make a break? I forgot.
Yeah, probably about now.
Yes. So for now, what I want you, please make sure that you are able to read the data, and then after, let's say 10 minutes, we can continue and see how can we apply our analysis in R. Okay? Okay, any questions? Either in person or online. Do you have any questions? Anything that you want to clarify?
Yes, hi. Could you go over again the directory here in the console, like how you access
Yes, yes. So what I said is that for R to know where kind of goes to find the data, first of all, you need to have a folder. Here I have a folder where I save the data and also the R script in the same folder. Okay, and then what you have to do is you need to tell R where to find the data set, and this is where you're gonna set the working directory. One way to do it is if you know the location, the path of your directory, you just use the function setwd, and then inside you specify the location where is basically the folder with the dataset and the R script. Okay. Usually I try to avoid that because if you go from Mac to Windows, you may need to change the backslash to /. There are different things. So usually what I'm doing is I'm doing it manually. And how you do it manually? You go session, set working directory to source file location. Are you able to find those on your laptop? So session, set working directory to source file location. So what you are saying basically here, you are saying to R that the working directory where you can go and find the data set are in the same folder as your code. Okay? So you need to have the code, the R script, and the data in the same folder. And then you just click to source file directory. And these now R will know where to find the data. So were you able to do it? I guess it was Christopher, right? Were you able to set the working directory?
Yeah, I'm just moving the files right now. It's running a little slow.
Yes, just bring the R script and also the data into the same folder. Open the R script here, and then go session, set working directory to the source file. And as I said, the first step that we need to do is we need to read the data set. To read the data set, we're going to use the read.table function. Now, you can see that I already read the data. Here are in my environment. Now, another important thing that you may need to know is how to clear the RStudio, the R code, the console, and also the environment. How you do it, so you see that button here, which is called clear objects from the workspace. I suggest anytime you start doing a new data analysis or you want to redo an exercise, I suggest first clear, let's say, the environment, just to make sure that you have the correct data set. Because maybe you did an analysis, you modify something, but you want to make sure once you restart the data analysis, you are using the correct data set. So what I'm suggesting is you go here, let's say you clear the objects, then you can even go to edit and then clear the console. These will clear everything, basically. We'll clear the environment, we'll also clear the console, and then we can start from the beginning and let's say run the commands. Now the first command is, let's say, read the data. You can see that I read the data, I call them clusters. I gave a name to the data set. There are 123 observations and 11 variables. If you click on that play here, you can see the different variables, and then the type of the variable, and then some results from that, some observations, the first observations from those specific variables. Okay, now there is also a command called head. If you use that command for the data set, then here you can get an idea of how the data look like. So here, I want you to observe that, okay, I have those specific variables. I have the clusters, that's basically the name. I have the park, I have the type, the top speed, the maximum height, the maximum drop, the length, the age, design, inversion, and the number of inversions. So here we get an idea of the first 6 lines of the data set, how the data look like. Okay. Now let's assume that I want to investigate and get into, try to understand the top speed of the roller coasters. So here, what I'm going to do is, I'm going to go in the data set. Okay. We have the data set to be coasters, right? I gave this name, coasters. To get a specific variable, a specific column in the data set, you can use the $sign. So you have the name of the data, and then if you add the $sign, then it will show you all the 11 variables that you have, all the 11 characteristics that you have about the roller coasters. And let's assume here that I want to get more information about the top speed. So what I'm going to do is I'm going to use a function called summary. So that's a very standard function in R, which usually you get some summary statistics about a variable. So if you have a quantitative variable, so here the top speed is a quantitative variable, is taking numeric values, then the summary will give you what we call the 5-number summary. Actually, it's giving you here the 6-number summary, which you have information about the minimum value, the minimum speed, the first quartile. So that's telling you below that value, I have 25% of the observations. You have the median, is telling you below that value, I'm going to have 50% of the observations. I have the mean. We already seen what is the mean. The third quartile, below that value, I'm going to have 75% of the observations. And then you also have the maximum. Okay. So this is giving you an idea of how the data look like. Okay. I can also get just the mean. So you can use the mean function. So again, I'm getting my data. I'm choosing the top speed. And then I'm using the function mean in R. If you run this command, now I get just the mean. Okay, so here you can see the 5-number summary, the summary, but if I want to get the mean, I can just use the function mean. I can also use the standard deviation, right? So the mean is telling you, on average, I'm expecting the roller coaster to have a speed of 56, I guess miles per hour, right? I want to see how spread are the values around that typical observation. You can use the standard deviation, and the function for calculating the standard deviation is the SD. Okay? If you run this command, then you can get the standard deviation of 12. Now I know the typical top speed is around 56, and then I know that the observations are spread out around 12 miles per hour around that typical observation. So in other words, it will not be unusual to have a roller coaster that have a speed one standard deviation, let's say below or above the mean. Now I can also create a histogram. You remember that if I want to see what's the distribution of my variable, here I can use the function hist. That's the function in R to create a histogram. Again, as a first argument, you can specify the data. Again, I'm getting the top speed. And then here I'm also giving a name to the x-axis. I'm going to name the x-axis as the top speed. Okay? And if you run this command, then we can get the distribution of the top speed. Okay? So you can see that on average, the typical value is around here. And then I see that they're kind of symmetric, right? It's kind of symmetric, unimodal, and kind of symmetric around that typical observation. Okay? So this is how we get a sense about the variable. Do you have any questions? Now let's start exploring the relationship between two variables. Now let's say I want to see what's the relationship between the speed and also the maximum height of the roller coaster. Maybe I want to investigate that relationship. I have two quantitative variables. I have the speed of the roller coaster, and now I also have the height of the roller coaster. I want to remind you to visualize the relationship between two quantitative variables. We can create a scalar plot. And this is what I'm doing here. So here I'm using the function plot. As a first argument, I'm going to have the maximum height. As a second argument, I'm going to have the top speed. And again, I'm just renaming the x-axis and the y-axis. And then if I run this command, then now you can see in that window here, we get a scatter plot for the relationship between the maximum height and the top speed. Now, what do you observe? How can we describe the relationship between the maximum height and the top speed? I want to remind you, you need to comment about different things, right? The direction, positive, negative, or no, let's say, or neither. I need to comment about the form. Is it linear? Is it curved? There's no pattern. Are there any outliers? And let's say, how strong is that relationship?
You have a comment.
Okay, someone said online, yes. So is it positive? Okay, I have a positive relationship between the variable. Now, is it, okay, fairly strong? Yes. You can see that the points are quite close to one another. Is it a linear or is it a curve? Can someone else online said, is it a linear or is it a curved relationship between these two variables? Okay, it's a linear. Yes, I can see that the rate of change of the speed is somehow constant as I'm increasing the maximum speed. Okay, that's good. Now let's calculate the correlation. Let's find the actual correlation between the two variables. So there is a function called core. Okay, I'm choosing my two quantitative variables. For correlation, it doesn't matter which one comes first, which one comes second. We're going to get the same correlation. And then actually we can see that the correlation is 0.85. So here we have a pretty strong linear positive correlation between the variables. Okay, now let's go and feed the linear model. Okay, let's find the best line that can be passed through the data points. So to feed the linear regression in R, I'm going to use that LM function. Okay, so that's a built-in function in R. And then what you have to do is, as a first argument, here you need to specify what is your response variable. The variable of interest here will be the top speed. And I want to see how the maximum height affects or influences the top speed. So then I'm going to use that notation here. On the left-hand side, I'm going to have the response. And then on the right-hand side of the tilde, I'm going to have our explanatory variable, my predictor. Okay? And then I'm also going to specify the data set that I'm going to use. So here I'm saying R, that the data that we're going to use will be the clusters. Okay? And then we can run this command. And then we can see basically the result. What I suggest you should do, you should create an object where you can save all the information regarding the linear. And this is what I'm doing here, model_1. If you run that, then we can see that even in our environment, we have a model. We have here a model which is basically our linear regression. Now let's see the summary. I can use the summary to see the information that I'm interested to know about the linear regression. And what I want to know the intercept. So that's the coefficient for the intercept. And then I also want to know the estimation for the slope, right? So that's basically my slope. Now here you can see the standard error. Do you remember we talked about the standard error? And then you can also see the p-values. So here I have the p-values for the coefficients. For the simple linear regression, we mainly care about the p-value and the coefficient for the slope. So these will give us an idea of the relationship. And we can see here that I have a positive relationship between the two variables, and also the p-value is significant. So it really, let's say the maximum height really affects or influences the top speed. Now let's add the regression line into our scatter plot. So here I'm using the upline function, and then you need to specify the model. And if you run that, then you can see that now, and you can even zoom here, and you can see that now I have a scatter plot, and I also have the best line that can be passed through the data points. Okay? So this is how we feed the linear regression. Now you can also do predictions and the residuals. So I'm going to skip that these few lines for now. Now let's see, how do we make predictions to new variables? Our goal for the linear regression is not just about finding, let's say, characterize what's the relationship between the variables, but I want to be able to, let's say, if I get a value for my explanatory variable, to give me an estimate, to give me a prediction about the response. And this is what I'm doing here. So here I'm going to use the predict function. Okay? You need to specify the model that you're going to use. Here we're going to use the simple linear regression. That was the model underscore 1. And then you need to specify the new data, the new data set that you're going to use for predictions. And here the way to do it, so R is taking specific type of data. So here I suggest you need to use the data.frame. So data frames are specific type of data that are very useful in R. And then you specify inside the value of the predictor that you want to make the predictions. Okay, so here I want the max underscore height. That's the name of our explanatory variable. And then I'm saying that this is equal to 50. Now, one characteristic of R is that it works with vectors. So usually, so for this one, I guess, even if you don't use that C, it should be fine. So that C function is helping us to create vectors in R. So let's say if I want to create a vector, let's say maybe 1, 2, and 3. Let's say I want to create that vector. In R, you need to specify that C function, and inside, you need to put the values of the vector. So here, I just have a single value, so most likely you don't even need that C function, but have in mind that if you want to specify for more than one values, you need to have that C function in R. Okay? And then what you're going to do is, you're going to run this command, and then you can get, let's say, the new prediction for a roller coaster with the maximum height of 50. So you can see that for a roller coaster with a maximum height of 50, that's the predicted speed, top speed that I'm expecting for that specific roller coaster. Okay? So this is how we make predictions using the simple linear regression. Okay? So basically how we use the model, we go here, we go up to the line, and then we can see what is our prediction. Now, apart from the simple linear regression, you can add some more variables in your model, right? And then we know now with the p-values to see if that variable should be included in our model or not. So this is what I'm doing in the second model here. So I'm defining with model. Okay, so can we show again where the slope and p-values were in the model 1 summary? Yes. So from the summary, the information that you need to know first are the estimates. So this value is our beta 0 hat. That's our y-intercept. This one is our slope. That's the beta 1 hat. That's the estimate for the slope. What are the things that you need to know? You need to be able to get those estimates. You also need to know the standard error. If you remember, if you go back, we define what is the standard error and why it is important to look at the standard error. And then it will also be of interest to look at the p-values. So these are the p-values. Okay? So the p-value is that the probability, that one, greater than the absolute value of a t. So these are the p-values that we need to look at the linear regression. Here you can also see some more information. If you remember, we talked about the residual standard error. We also talked about the R-square. So you can find them here in the summary of the model. Okay, so for the slope, these are the estimates. This is the standard error, and then this is the p-value. Okay, yeah, no problem. Now for the multiple regression, how do we define the multiple regression? You use exactly the same function as what we used before, but now, apart from the maximum height, let's say I also want to include the maximum drop. Okay? So what I'm going to do is I'm going to use the top speed as my response, and then I'm going to use that tilde, and then I'm going to have the maximum height plus the maximum drop. The rest exactly the same as what I had before. And let me run this command, and then we can get a summary. And now this will give you, okay, now I have a multiple linear regression I get the coefficients here. That's the y-intercept. That's the coefficient for the maximum height. That's the coefficient for the maximum drop. And then you can see the p-values to see if indeed these variables are statistically significant or not, okay? And you can even see the standard errors. Now, similar logic, you can even do predictions, okay? You can use the predict function to use that multiple regression, let's say to predict for new variables. Now, another thing that I want to mention here is that regarding the summaries, it is important in a lot of cases to look the R-square or the adjusted R-square to see if we should be including those variables, if our model is improved by adding, let's say, those extra variables. Also, you can add some categorical variables as the explanatory, and that's related to your question. So here, let's say if you have a response to be quantitative, okay, but then you have some variables that are quantitative, but then you also have some variables that are categorical, then you can use that factor function in R. Okay, so let's say I want the type of the roller coaster. I think here it's either wood or steel. So here, because you have two categories, then you need to specify, you need to use a function factor in R to tell R that you should treat that variable as a categorical. It's not a string, it's not a numeric, it's a category. So you can use that factor function, and then you can add that command in your model. So similar logic, I'm not going to get into the details here. So here you can see that I have a multiple regression where I use more than one exploratory variables. Similarly, you can apply a polynomial model. So let's say here I want to add a model, not just, let's say, here I want to have the maximum drop, but let's say I don't want to just have the length of the roller coaster, but I also want to test the square of the length. Okay? Maybe you create a scatter plot, you see there is a curve relationship, and then I want to add the square of the length. That's the way to calculate, let's say to model, to feed the polynomial regression, okay? So you define a new variable, so you have the data, you define a new variable which is the square of the length, okay? You define it as the length square, and then you use the same function to define the polynomial regression, okay? So I know I'm kind of covering them quite quick, these things. If you have any questions, feel free to reach out if you want to clarify for any of those different linear regressions. Okay, and now let's go to the logistic regression. Let's see how do we fit that in our studio. So let's say first, I want to see if there is a relationship between the maximum height and the type of the roller coaster. I want to see whether, let's say, it's a wooden roller coaster or is it steel, how it affects the maximum height of the roller coaster. So here I'm creating a scatter plot. So here you can see the observations for one of the type, and so here you can see the observations for the second type of observations. Now let's say I want to apply a logistic regression. I want to see, based on the maximum height, if I'm able to predict the type of the roller coaster. Maybe if it's higher, I have, I don't know, a roller coaster with steel, or maybe it's higher, I have a roller coaster with the wooden. So that's what I'm trying to investigate here. So to apply the logistic regression, there are different ways. So here I'm showing you one way to do it. Actually, let's go to the alternative way. So here you can see the alternative way. Now I'm using a different function. I'm using the GLM. That's the generalized linear model. That's a different function on what we had before. And then you have the type. The type is a categorical. We need to let R know that that's a categorical variable. It shouldn't treat the type as a character. Here I have two categories, either wooden or string. So I need to use the factor function and then the type. And then after the tilde, I'm defining what is my explanatory variable. Again, I have the data set that I'm going to use. And now be careful, for the family here, I need to specify the binomial family. If you specify the binomial, this will give you the logistic regression. There are different families here, there are different models, but for the logistic regression, you need to specify it as family to be the binomial. And then we can run this model, and then again, with the summary, you can get the coefficients, those beta. Let me show you in a lecture. So you can get those beta, right? Those beta 0 hat, beta 1 hat, you can get them here. So if you see the summary, this is our beta 0 hat, that's our beta 1 hat. Okay? And again, we can see whether that variable is statistically significant, if indeed it really affects my, let's say, response variable. Okay? Now, how do we make predictions? We can use the predict function. You use your model, predict the model, and this should give you a predictions. So here, let me do predictions for a new variable. So let's say I want to find, for a roller coaster that has a maximum height of 30, I want to see whether that roller coaster is wooden or it's a steel. So what I'm going to do is, I'm going to use that function, predict. I'm going to run this command. Okay, so this one is giving you, so this value is giving you here, this one, is giving you the linear combination of the variables and the coefficients. So what I have to do is, once I get this value, I need to go back in our formula, e to the power, the linear combination, divided by 1 plus e to the power of the prediction that you get. You run this command, and then you can see what is that probability. So this probability is 0.73. So it means that the probability that you're going to have that category, the first category, is 0.73. That's greater than 50%, so then you need to assign it, that specific observation, to the category, to the first category. And what is the first category here? The first category is basically the steel. So let me double check. And I think the first category here is basically the steel, yes. So in this case, the probability that it's 0.73, so it's greater than 50%. My success here is basically the roller coaster is made from steel. Okay? So let's say you can assign that specific roller coaster to, let's say, the steel category. So you are able to predict the category in this setting. Okay? So someone can, I'm getting 0.26. Now, if you get the other one, 1 minus this probability, then it's basically how you define the categories. Okay? So you can either get 0.73 or 1 minus 0.73. So it depends how you define the categories. Okay? So in this case, how I define the categories was the steel, was the first category. So that probability is for the steel category. This is my success in this setting. Okay? So that's a very good question. So be careful how you define the categories, the two categories in, let's say, in your R. Okay? Any questions? Yes.
Can you go back to like the graph?
Yes.
Like the factors.
Yes. Okay.
Yeah, the factors. So like, I know it says like the scale 1 and 2. So what is exactly 1 and?
Yes. So what you could do, and actually, if you go in the R code, I'm showing you here how you can basically change the coding. So if you use the factor function in R, R will assign to one of the categories to be 1 and to the other category to be 2. But what we said is we prefer 0 and 1, right? Then what would you do? I suggest you use this function here where you assigning, let's say, 1 if it's a steel and 0 if it's a wooden. So if you run this command, okay, and then you create the plot again, now you can see 0 and 1. So these are the observations of wooden, and these are the observations for the steel.
That makes sense. Thanks.
Okay? So R is kind of randomly assigning some of the categories to be 1, some of the categories to be 2, but you can specify, let's say 0 to be the wooden, and then 1 to be the steel. Right? Okay? So it's up to you how you define the categories. Okay? And the way you define the categories will also plays a role regarding the probabilities here, right? So this probability is for the one that you define as 1, this will be the probability for that category. Any other questions? Okay, that's regarding logistic regression. So we have around 20 minutes. Now let's try and talk a little bit about some more advanced, let's say, machine learning techniques. So the first one is what we call the decision tree. So the decision tree is a supervised machine learning method often used for classification. What I mean by supervised machine learning technique is that I have a response. It could either be a numeric or it could be a category, and I have some input, I have some explanatory variables, and I want to see how they affect or influence my response. Okay? Usually, the response variable or the target variable will be a categorical. That's not necessarily true. For the decision trees, you can even have a numeric. Okay? But in most of the cases, we apply the decision trees anytime we have categorical responses. And now let's see what are the steps that we follow to apply the decision tree. So first, we select a target variable, a response variable, and then the predictor variables are analyzed individually, and the one that splits the responses the most accurately is selected. So in other words, we start with the whole data set, okay? All the variables in the data set. So what I'm going to do is I'm going to apply an algorithm where you're going to choose an explanatory variable that more accurately assign the observations into different categories. Let's assume you have 2 different categories, then have a lot of explanatory variables. The first step is I'm going to choose a predictor that separates most accurately the data into different categories. Okay? Now, how does decision tree does that selection? It uses what we call the entropy, or let's say the Gini impurity function. So basically, the goal is to make the data as pure as possible. So I'm going to choose a variable to split the data such that at the end, I'm going to have data, let's say from one of the categories. Okay. Then what's next? Additional predictor variables may be selected below, and further splitting the data to improve the accuracy of the classification. So once you choose the first variable, then what you're going to do is you're going to choose the second variable that again more accurately split the data into different categories. And what is the goal? What is the objective here? I want to split the data such that in each of the categories, I'm going to have observations from one category. Okay? And all this will make sense once we go to the examples. And then you are repeating that, you repeat that procedure until, let's say, you ended up with groups that have only observations from one category, or let's say you decide that that decision tree, you don't want it to be too long, and then you decide to stop the tree. Now the result is a flow chart where the data from new observations can be plugged in at the top, and predictions for classifications are made by comparing the predictor values with the optimal split in the tree. Now let's see an example so that we can understand what is a decision tree. Let's say we're back in our scenario where I want to see whether a voter will vote for Biden or for Trump in the 2020 election. The first thing that we're going to do is we need to have a response, right? So what is the response? Has 2 categories. You either vote for Biden or you either vote for Trump. So this is a classification problem. Now what we're going to do is I have different variables. Maybe I have information about what is their political party, where do they live, what is their education, maybe their age. Then what the decision tree algorithm will do is first it's going to choose the variable that splits better the data. So here, for example, if we choose the political party as the first variable, then in our data set, we're going to observe, let's say, that for the people that they're Democratic, 73 of them, they vote for Biden, 24 they vote for Trump, and then for the Republicans, let's say 41 voted for Biden, and then 82 voted for Trump. Now, that's a very good distinction between, let's say, the Biden voters and then the Trump voters. So you can see here the majority of them are Biden voters, the majority of them here are Trump voters. Okay? Let's say we're choosing that variable as our first split in the decision tree. Then next, what we're going to do is, for this split, we're going to consider, okay, which variable should I consider such that I'm going to split those observations better, in the sense that I'm going to have more pure groups at the end. I'm going to have groups that have only Biden or only Trump. And let's say here, for the Democratic, if I ask where do they live, whether it's an urban, suburban, or rural, then it's giving you the following results. Let's say 50 of them, they vote for Biden, 4 of them, they vote for Trump. Rural, again, 23 Biden, 24 Trump. Okay? And then you're doing that, same for, let's say, the Republicans. Now, what is the variable that is splitting better the observations? Let's say for the Republicans is whether or not they have a college degree. So in this case, I'm use that variable, and then you can see 40% Biden, 48 Trump, 1 Biden, and then 34 vote for Trump. Okay? And you keep doing that. So let's say for this one, then you can keep doing, and then what question you need to ask such that at the end you want to have as pure results as possible. Let's say at the end you want to have a result where you're going to have either Biden or Trump. Okay? Does it make sense? Like the intuition behind the decision tree. So we have a target, it's a categorical, and then you choose the variables that are more important in the sense that they're making most of the distinction between the observations. And then you keep doing until you decide to stop. In a lot of cases, you decide not to have a very long tree. You may decide to stop after 2 or 3 repetitions, or there are other, measures that you can decide where to stop the decision tree. Can you think of any benefits of the decision trees? Let's say compared to the linear model. Or let's say the logistic regression, right? Logistic regression is related to classification.
At least when taken to a larger extent than just like 3 questions, you essentially create a field of probability rather than a line or an you can extend across an entire area.
Yes. So what you are saying is, if I understand correctly, is that what you mean is that you can much easier interpret the results from the decision tree, right? Now I have a clear map, a flow chart, where I can easily explain, even to someone with no statistical background, I can follow, this follows like the human logic, right? So it's some questions, you follow the diagram, and then at the end, I'm gonna say that here, if you are in that part of the tree, then you are Biden voter. If you're on that part of the tree, you are Biden voter. If you're on that part, you're a Trump voter. So I can easily follow the diagram and get my prediction, right? So it's very easy to explain, even to people that they don't have any statistical background, and it's a very nice graphical way, and it's also, you can easily make predictions, because what predictions is like, you go to the doctor, right? It asks you, how do you feel? Did you take this one? And then basically you follow that diagram, and then you ended up, let's say, with one response. Now let's go in R. So I have 10 more minutes. Now let's go in R to see how do we apply the decision trees. And then we can briefly talk about the k-means clustering. So here, if you go, you can see the decision tree part. Now, I want to point out one thing regarding R. R has some built-in functions, but there are also some other functions that they can extend the ability of R, but you need to install those packages. So what I suggest, what you should do is, first, you need to run this command. So to do the decision tree, first you need to install the package called rpart. You just need to install it once, so you don't need to install it anytime you access R. So you install the R part package. You also install the rpart.plot package. These you just run the commands once, so I'm not gonna run them because I already installed them on my computer. So you run these commands once, be patient, it may take a while until it installs, and then we need to load those packages into R, and I'm gonna use that library command. If you click those, after you install, if you click the library, then you're gonna load all these functions, all these new functions to the R, and then we should be able to use them. And here I'm using a function called rpart. And let's assume that, again, I want to classify the different type of roller coasters, but now I want to use more information. Here are more variables. I want to use the speed, the height, the maximum drop, the length, the age, and the design. So again, I'm using the same format as what I had before. I have my response, and after the tilde, you're gonna have your explanatory variables, and again, you have the data set. You run this command. The good news is that R now will create the tree for you, the decision tree for you, and now let's plot the tree. Let me make it big here, and let me run this command. And now we can see basically the decision tree. Okay, so this is telling you that, okay, so I have the data set, I have the whole data set. So in the data set, I have 79 coasters that are made from steel. The first question that you need to ask to decide whether the coaster is from steel, is made from steel or wooden, is the maximum height greater or equal of 128? If the answer to this one is yes, then you need to assign it as a steel. Okay? So your prediction for that specific roller coaster is basically steel. Now, if the answer to that one is no, then you have another question here. The question is the length of the roller coaster less than 2,621? If the answer is yes, then you go in that part of the branch. And then you keep asking questions, and then you ended up to those final steps where you're gonna conclude whether your coaster is, let's say, from steel or the wooden. So basically it's like questions. You follow that. After this question, you get into that branch. Is the age of the roller coaster less than 49? If yes, it's a steel. If no, it's a wooden. Okay, and you do that same thing to make predictions. Okay? So very easy. Tell me the information from the roller coaster that you want to predict, and then I will follow this graph, and then I can tell you what is my prediction for the type of the roller coaster. And you have a very nice visualization of your model in this case. Okay? And that's a decision tree. I didn't really define the model beforehand. I let the algorithm decide about the format of the model. So that's what I'm saying about the flexibility in the machine learning techniques. I didn't pre-specify the model. I didn't tell them which variables to use. I just give all the possible variables, and then based on the data that you have, based on the variability, then the machine learning technique is giving you that specific technique, and that specific, let's say, model. Okay, so that's regarding the decision tree. So we can apply the decision tree anytime you want to do a classification. Anytime you have a categorical variable, and then you want to assign them, let's say, the response into different categories. Okay. Now, the last one, in the last 5 minutes, let's also briefly talk about the k-means clustering. Now, what is a clustering? It's a method of partitioning the observations into groups, into clusters, where each observation is assigned to a cluster with the nearest mean. Now, the k-means clustering is an unsupervised machine learning technique. What do we mean by unsupervised machine learning technique is that I don't have a target variable. I don't really have a response. It's not like I want to see if it's a wooden or if it's from steel. I don't want to see what is the average price. I don't really have a target variable in this setting. So here what I'm doing is more about doing an exploratory data analysis. I have my data. I want to see if there's some kind of grouping between the data. Okay? Now, what are the steps here? Okay, so the steps that we follow in the cluster. So the first step that you need to do is you need to pre-specify how many groups do you want to have. Okay, you want to have 2 groups, do you want to have 3 groups? And then what the algorithm is doing is that once you specify the groups, and actually let me go now to the examples. So let's say here I have this data set, and let's say I want to have 2 clusters, 2 groups. Once you specify the groups, then what R will do, what this k-means algorithm will do, will randomly pick 2 points, okay, in the data set. Okay, let's say choose this point and maybe this point. And then it's going to take the distance of all the points to that specific observation. And then it's going to merge them together into different groups based which ones are closer to that random point that you have. And then you're going to repeat that observation, we're going to repeat that, let's say, step again and again. So let's say first you choose maybe these 2 points, you create some clusters. Once you create the clusters, you get the average distance of the clusters, and then you get a new data point, and you keep doing that, you keep doing it until, let's say, you get the 2 groups, the groups that they are closer to the center. That's the center, let's say, I think we call it centroids, yes? So basically these are the means of the cluster. And then depending on how many groups you want to specify, let's say the same data set, if you specify 2 groups, you may get those 2 clusters here. If you specify 3 groups, then you may get those 3 clusters using the k-means, okay? So here you have these groups, all of them are the closest one to the center of the cluster. And now let's go and see how you can do that in R. I want to say about the clustering that is more challenging than regression, than classification, because I don't really have a target variable, and it's kind of subjective. I don't really have a clear thing to compare to say, okay, why there should be 2 groups or there should be 3 groups. It also needs to have a lot of expertise in that specific area. And to do the k-means clustering, again, we need 2 more packages. The first package is what we call the ggplot2. Okay, you mentioned before about the ggplot, so you can also use that in R. So you need to install the ggplot, the factor extra. You need to load these. Okay, so you install them once, and then you load them into R. Now let's say I want to apply the clustering in that specific data set. So I want to have the top speed and the age of the, let's say, of the roller coaster. So let's see the data set. So here I have the top speed, and then I have the age. Now, I want to see if there's any kind of grouping in the data set, in the sense that, you know, the older the roller coaster is, I see that it has maybe smaller top speed, right, compared to maybe some new roller coaster, right? I want to see if there's any kind of grouping in these variables. So what I'm going to do is, I'm going to use the function k-means. K-means, you need to specify the data. Here, the top speed is in the 4th column, the age is in the 8th column. So this is how I choose my data. And then let's say I want 4 groups. I want to create 4 groups in our clustering. So I run the k-means, and then I can use that command fvis_cluster to see the different clusters. Okay, let me make it, okay, where is that? Okay, so it's here. So now we can see that by using the k-means, now I have some clusters from the data. So we can see that these observations, they may have some characteristics that they're all together. And actually, if you observe, these are the ones that they're the older one, the oldest one. The older the roller coaster, I see that it belongs to the lower half of the top speed. Then if you go to these observations, maybe to the younger one, here you can see that, okay, I have, again, 3 different groups. I have the ones that they're newer one, but they have low speed, middle speed, and then they have the high speed. Okay? So again, there's some kind of grouping between the variables. And these numbers basically represent the observations. Okay? Now you make some kind of exploratory data analysis in your data. Do these groups make sense? You really need to have an idea of the data set and be able to, maybe based on your knowledge, okay, you can say, oh, these ones, they are specific kind of roller coaster, these ones are specific kind of roller coasters, and similarly for the other groups. Okay? So I think I will stop here for today. So I know we're covering a lot of things. If you have any questions, feel free to reach out. So I'm more than happy to help you through emails or even talk to you like office hours, through Zoom, to go in more details regarding those techniques. Okay, so I'm gonna stop here for today. Thank you very much and see you in 2 weeks.